Okay, so for the physics test, resources you can use. You are definitely going to be able to use your Big 5 chart. Okay, I say Big 5. If you've got Big 5 number 6 on there, you're also welcome to use it. If you need Big 5 number 6, then I can track it down and I can show it to you. Other formulas and whatnot you're going to be able to use. You can definitely use your trig cheat sheet. It should hopefully be tucked into your calculator. Anything like, does Big 5 chart have just velocity equals displacement divided by time? I think so. Let me check, I got mine right here. Yeah, velocity equals delta x divided by delta t. Average velocity. So yeah, using your Big 5 chart, it's got that on there. Trying to think what else. Anything like constants, I'll have up on the board. I mean, the main constants you need to know is like acceleration due to a falling thing from gravity is 9.8. The gravitational constant is at 6.67 times 10 to the minus 11. I'll have that posted somewhere. Gosh, there's that many other things. Of course, any of the formulas I've got up here, like formula for torque, okay? Formulas for friction. Newton's second law. Okay, force equals mass times acceleration. Force of gravity. No, we've used more formulas than that. What am I forgetting? Maybe that's all we've done. Is we just spend a lot of time on Big 5 stuff and then came here. Have I handed y'all any other reference charts or any other formula charts? Okay, I didn't think I had. So.
Oh yeah, we have that chart.
What chart? That?
Line chart.
Heck yes. Let's say if you got that chart, you can use that. So lines on graphs, which I think is like, is that a picture of a cheetah in the background?
Yes.
Okay, so this is your cheetah. Is there anything else? I did say you have to keep those. Let me look at that. I may just say, hey, if you want to use one of these dudes, I will have these dudes. Yeah, if you want to use one of these, you're welcome to. Okay, let me put the green star physics chart. Not bad, right?
We did all 6 of the units.
Yeah, could be worse. We're actually on target. I'm fairly impressed by that. Yeah. And the spring semester is so much more fun. We got a little bit of math to get through, then we get into all kinds of fun things like waves. Waves are awesome.
Oh, I do have it.
Yeah, cool. So if you don't have any of, or if you're missing one or more of any of these, let me know and we'll track you down copies before.
I need to trade cheat sheet because they made us take them off at calculations.
Those heartless, soulless, cruel individuals. I bet I got a cold roll call them. whole drawer full. I got one here. I can make more though. Y'all just let me know what you do need, and I'll make some more. So who needs a big 5? Okay, I got some. Okay, now that I know I got. I got. All right. Okay. Who and what and how? There you go. There you go. There. Anybody else? Any big 5? Okay. I got you. No, wait, actually. All right. Okay. I never actually handed out a paper with torque and friction and second law and gravity on here. So I'll probably just leave these up if that's okay. Plus they should all be on your green chart if you use a green chart. Yeah, let me pause. Okay, so Avis, what would you like to know about projectiles? Oh, come on. All right, well, I mean, besides what I've got on the thing here, is the vectors thing a thing you want to talk about, or just like projectile motion examples, or what?
Yeah.
What's the difference between like when it's getting dropped off something and when it's
All right, perfect. Okay, so we'll talk 3 situations here. Okay, situation 1, you got a cliff. Somebody just lets go of a ball and it falls straight down. Right, that's free fall. Thing you need to keep in mind when you've got a projectile, if you are just considering the y portion, an object that is in projectile motion and just the y is always in free fall. So it's just like dropping the mic, dropping the marker, dropping the ball. This part of the projectile is always going to be going according to the forces that it's falling. Now it could be that it starts falling because somebody in situation 2 decides to launch it horizontally. Now if it's launched horizontally, this over here still holds true. It's still going to start falling and falling faster and faster. It's just that while it's falling faster and faster, it's also going to be moving forward. Okay? The falling part doesn't change. Third situation, and I guess we could actually talk fourth situation because we never actually looked at the fourth, but it could be a thing, is that, let me actually bring this down. Somebody could take the object and they could decide to launch it upward at an angle. Okay? If that happens, then you've got to take its flight path and you've got to split it into 2 parts. The first part is when it is moving up. The second part is when it's moving down. Right? Fourth situation we've not really talked about at all is, let's say that somebody's got an object and they decide to throw it at a downward angle, right? Instead of throwing it upward. Well, all that that's going to mean is that, after they throw it, it's still going to be falling. It's just not going to be falling from a starting speed of 0. It's going to be falling from a starting speed that is greater than 0. Okay, and you're up and down. But that's just all considering the y part of it. The y part of it, you are just looking at an object in the up dimension and the down dimension that is in some kind of free fall. Either, like if it's doing this dude right here, then the first part of its flight, it is in free fall and it's slowing down. Second part of its flight, it's speeding up. Everybody else, if it's in a free fall situation, it's speeding up as it falls faster and faster because the only thing pulling on it at this point is gravity, and it's pulling on it with a downward acceleration of 9.8 meters per second per second. Okay? That is just considering the up and the down. The forward and backward is much easier. Okay? Let's look at these situations again. If I consider the x, if it's just being dropped, x equals nope. Meaning that it's not moving this way, right? You're just concerned with the y component. If it's this right here, then whatever its velocity is that it's thrown at to start with is going to be equal to whatever its velocity is going forward when it hits. Because velocity of x is constant. In fact, it's constant here. It's just that velocity of x equals 0. It's just not going back or forth. Same thing here. If you take this starting thing, now this right here, I think the thing that still gives people a heart attack for some reason is when you look at a starting vector, whether it's upward or whether it's downward, you can take this and you can take it apart. And when you take it apart, it's got an x component and it's got a y component. Right? This x component right here, whatever it is right there, it's going to stay the same. Whether it's here, let me clone that. It's going to still be the case when it's up here. It's still going to be the case when it's right here. Because that v of x is constant. If you don't have that. If you don't have air resistance. And we're assuming we don't. Okay. Same thing right here. If you've got a downward vector. Well, check it out. You can still take that downward vector. You can turn it into an x component and a VO of y component going down. But this x component right here, the entire time it's falling, does not change. It's going to stay the same, bless you. Okay? So, when you get a projectile motion problem, and I promise you you'll see some, understand that what we just talked about holds true. The y, once it's out of somebody's hands, it's being pulled down at an acceleration of 9.8. The x is whatever it was when it left the gun or the cannon or the hand or whatever flung with it. And it does not change. Does anybody remember for me, when you've got a projectile motion problem, my first suggestion is always make a picture. Does anybody remember what my second suggestion is?
XY chart.
The XY chart. Okay, make a T-chart with X on one side and Y on the other. List what you know. And usually the most important thing to find if it's not given to you is what? Time. Exactly. Because hang time, time it's in the air, is the same for both X and Y. So if you can find time, time is like the bridge that's going to, that's a terrible T. Time is like the bridge that's going to help you get from one side of this chart to the other. Find whatever it is you need to find. Okay. That's my pep talk on projectile motion. That's very general. Do you have any specific questions regarding the hows or the whys or any of that? I find time? Well, I pick whichever one of these has what I need and doesn't have what I'm not given. Okay, looking at your big five, out there to the side where it says doesn't use, whatever it is it says it doesn't use, that's usually one of the ways that I know which one of these I can use, because I take what I'm given, I take what I'm looking for. If they don't mention acceleration at all, I use big 5-1. If they don't mention starting velocity at all, I use big 5-4. Okay?
This is the one where acceleration is always 9.8 unless it says differently, right?
If something's in free fall, acceleration is always 9.8.
Great.
Okay. If it's like a car that's accelerating down a hill, or a skater who is slowing down at a constant rate or something like that, or constant acceleration, then either you calculate the A or they give you the A and you find something else. Okay. But see, you notice the big 5 started back in unit 3, right? Because we were using big 5 before we ever got to free fall, before we ever, well, not far before we got to free fall, but before we got to projectile motion. Anything else while we're on the topic of Unit 4 or projectiles that you've got a question about there? Going to pause. All right. So back in Unit 2, we started talking about different ways of representing motion and acceleration. Okay, and we took a look at a distance, or actually not so much distance, displacement. Versus time. Okay, a displacement versus time graph, what you do is you have, now, here's the thing, on any of these graphs, what's always going to be on your x-axis? Time is, okay, exactly. Because time is not the thing that you are, yeah, I mean, it's changing by itself, right? Okay, you're not able to manipulate it, sadly. That would be cool. Okay, it's just you're observing something else about the object that you're studying as time passes. So time is always going to be on your x-axis. If you've got displacement, then you set something as an origin point, and you call that origin point 0. Okay. If you've got something that has an upward slope like this, that means that it is moving away from the origin point in the positive direction at a constant rate. Okay? If you've got it then doing something like that, what's happening to it? I don't like using the word accelerating here. Okay, actually it's not doing much acceleration. There might have been some acceleration at this one point right here, okay, because the velocity changed, right? It's still moving away. Like you say, though, it's not moving as fast. Okay, now change happens again. What's it doing now? That's terrible. Yeah, it would be if I could draw a straight line. Let's try that one more time. If it's horizontal, then it's not getting any farther away. It's also not getting any closer. So what is its velocity at this point? 0. So right here, v equals 0. Right through here, my velocities are going to be positive. Now, starting here, let's just do that. What's happening in this last time interval here? Why? Meaning it is getting closer to where we started, so our velocity is negative. Remember, big thing to keep in mind, and I think I made a note of this, positive and negative equal direction. So who decides what direction is positive and what direction is negative? You do, the physicist. Exactly right. Okay. As long as you've got a dimension where you got that away and this away, one of those has to be positive, one of those has to be negative. Doesn't matter which one. Okay. Now, we've also got, this was a displacement versus time graph. Here we're going to have a velocity versus time graph. Now, if we go ahead and we have times set for each of those changes right there. Okay? Then I'm going to have those same time intervals being reflected right here, and right here until we get out to the end. So, let's go ahead and do the easy one first. Oh, but wait a minute. Here, we're going to actually have to put our 0 in the middle of our graph. Okay? Because we have some portions where our acceleration is negative. So, let's call this time interval 1, time interval 2, interval 3, and interval 4. And let's go ahead and graph what the velocity is during time interval 3. Is 0. So here in time interval 3, it would be that right there. Okay? Now it's going at a constant velocity in all of these other ones, right? So in time interval 1, is it moving faster or slower than it is in 2? Faster. But it's positive. So in time interval 1, it might be up here. It's going to be a little bit slower from there to there because they're constant. Now how about time interval 4? It's negative, so it's going to be down here. How far it is down here depends on how fast it is. Would you say that this slope is more severe or about equal to that first one? Might be more severe, okay. Which means that however far away I am right here, I'm going to be farther away the other way down here during that last part where it's negative. Now, most things don't do instant speed changes, right? So what you'd probably more likely be looking at is something more like a curve happening here. And if there was more like a curve happening here, that means it's constantly accelerating. Then you would see something more like that in your velocity. When you've got something like, if you've got a straight line like this, you have no acceleration, okay? All of these are at a constant v. When you've got an upward slope, that is acceleration happening. And in fact, this is going to be positive acceleration because it's increasing the velocity in the positive direction. We are sadly just about out of time. Don't have time to talk about the last graph, but if you'd like, we can pick up there tomorrow. So, y'all look these over tonight, come up with a list of some stuff you want to talk about. And I will see you then.